Imagine you're standing at what you think is the edge of everything that exists. You reach out to touch this cosmic boundary, and your hand passes right through. Because here's the mind-bending truth that's kept cosmologists arguing for decades. The universe can be infinite and still have an edge, but not in the way you think. What I'm about to show you will literally change how you see reality itself. And if you're ready to have your mind completely blown by the deepest secrets of the cosmos, then smash that subscribe button to the Lazy Cosmos right now, because we're about to embark on a journey that will shatter everything you thought you knew about the universe. Trust me, by the end of this video, you'll never look at the night sky the same way again, and you'll understand why some of the greatest minds in science have called this the most beautiful paradox in all of physics. Let's start our incredible journey 4,000 years ago, when humanity first dared to ask the question that would haunt us for millennia. Where does everything end? Picture this. You're a Babylonian astronomer standing on the flat rooftop of a ziggurat in ancient Mesopotamia, staring up at the endless dome of stars above you. The ground beneath your feet stretches out to the horizon in every direction, appearing perfectly flat, and above you, the heavens seem to form a great celestial bowl. To these brilliant minds, the world was a flat disk floating in a cosmic ocean, with the dome of the sky arching overhead like a giant umbrella. But here's what's absolutely fascinating. They weren't just making wild guesses. These astronomers were meticulous observers who tracked the movements of planets with incredible precision, creating mathematical models that predicted eclipses and planetary positions centuries in advance. They saw the horizon as a clear boundary, a definitive edge where the world met the sky, and it made perfect sense. After all, when you look around you right now, doesn't the world appear flat? Doesn't there seem to be a clear line where the earth meets the heavens? The Babylonians developed what historians call the Enuma Elish cosmological model around 1500 BCE, which described the universe as emerging from primordial chaos through divine conflict. But beyond the mythology, their practical astronomy was extraordinarily sophisticated. They divided the sky into three ways: the ways of Anu, Enlil, and Ea, each containing specific constellations and celestial phenomena. They tracked the movements of what they called the wandering stars, the planets, with such precision that they could predict their positions months in advance. Yet for all their mathematical brilliance, they conceived of the cosmos as fundamentally bounded. The Earth was a flat disk surrounded by the salt water ocean, and above stretched the solid dome of heaven, studded with stars like jewels embedded in a great crystalline vault. Beyond this cosmic architecture, they imagined realms of the gods. But these were not part of the physical universe as they understood it. The edge was real, definite, and absolutely fundamental to their worldview. But the human mind has this incredible hunger for deeper understanding. And it was the ancient Greeks who first began to seriously challenge these seemingly obvious conclusions about cosmic boundaries. Enter Eudoxus of Cnidus, a mathematician and astronomer who studied under Plato himself around 380 BCE. Now, Eudoxus wasn't content with simple explanations. He was obsessed with mathematical precision and geometric beauty. He looked at the complex dance of planets across the night sky and realized something profound. If the Earth was truly at the center of everything, and if celestial bodies moved in perfect circles as divine objects should, then he needed exactly 27 interconnected celestial spheres to explain all the observed motions. Think about the audacity of this concept. Eudoxus was proposing that we lived inside a nested series of invisible crystalline spheres, each carrying different celestial objects, all rotating at different speeds and angles. It was like imagining the universe as the most complex mechanical clockwork ever conceived, with Earth sitting motionless at the very center, while 27 invisible spheres wheeled around us in perfect mathematical harmony. The genius of Eudoxus's model wasn't just its mathematical elegance, it was how he grappled with the fundamental problem of cosmic boundaries. Each celestial sphere in his system had a definite radius and rotational period, calculated from careful observations of planetary positions over many years. The Moon occupied the innermost sphere, followed by Mercury, Venus, the Sun, Mars, Jupiter, and Saturn, with multiple spheres for each to account for their complex apparent motions. But what fascinated Eudoxus most was the outermost sphere, the sphere of fixed stars. This sphere, he calculated, must be at least 10,000 times farther from Earth than the Moon to account for the fact that the stars showed no observable parallax as Earth moved through its daily rotation. Here was a man in the 4th century BCE proposing cosmic distances that stretched the imagination to its breaking point, yet still insisting that the universe must have a definite outer boundary. Aristotle, that towering giant of ancient philosophy, took Eudoxus's model and said, "Hold my olive oil, I can make this even more precise." Around 350 BCE, Aristotle expanded the model to include 55 celestial spheres, each one necessary to account for the increasingly detailed observations of planetary motions that Greek astronomers were making. But here's where it gets absolutely mind-blowing. Aristotle wasn't just adding spheres randomly. He was grappling with a fundamental problem that still puzzles us today. How can we have a universe that's complete and perfect, yet also bounded and finite? Aristotle's solution was both elegant and terrifying. He argued that the universe must be eternal and unchanging, with a definite outer boundary marked by the sphere of fixed stars. Beyond this outermost sphere, he claimed, there was literally nothing. Not empty space, not darkness, but absolute nothingness. Can you imagine trying to wrap your mind around that concept? What does it even mean to have nothing beyond the edge of everything? Aristotle was essentially proposing that if you could somehow travel to the edge of his 55-sphere universe and stick your hand out past the boundary, your hand wouldn't encounter empty space. It would encounter the complete absence of existence itself. No space, no time, no possibility of anything existing. This wasn't just a physical boundary like the edge of a cliff. It was an ontological boundary, the absolute limit of being itself. Aristotle argued that, beyond the heaven, there is neither place, nor void, nor time, making the cosmos a unique, self-contained reality with literally nothing outside it to define an outside in the first place. The implications of Aristotelian cosmology were staggering and shaped Western thought for over 1,000 years. If the universe was finite and bounded, then every location within it could be defined in absolute terms relative to the center and the circumference. Earth occupied the unique position at the exact center of everything that existed, making humanity cosmically special in the most literal sense possible. The celestial spheres provided a hierarchical structure to reality itself, with the outermost sphere of fixed stars representing the boundary between the material cosmos and the realm of pure form and divine intellect. This wasn't just astronomy. It was a complete metaphysical system that explained not only where everything was located, but why it was located there and what it meant for human existence. Now, here's where our story takes one of the most dramatic turns in the history of human thought. While Aristotle's Earth-centered model dominated intellectual discourse, there was one brilliant Greek who dared to propose something so radical, so counterintuitive, that it wouldn't be taken seriously for another 1,800 years. Aristarchus of Samos, working around 270 BCE, made a proposal that must have seemed absolutely insane to his contemporaries. What if the sun, not the earth, was at the center of everything? But Aristarchus didn't just flip the cosmic order. He grappled with the mind-bending implications of his heliocentric model in ways that reveal him to be perhaps the most visionary astronomer of the ancient world. As the great mathematician Archimedes recorded in his work, The Sand Reckoner, Aristarchus proposed that the sphere of fixed stars is so great that the circle in which he supposes the Earth to revolve bears such a proportion to the distance of the fixed stars as the center of a sphere bears to its surface. Do you realize what Aristarchus was saying here? He was proposing that the universe was so incredibly vast that Earth's entire orbit around the sun, a distance we now know to be 186 million miles across, was essentially a single point compared to the distance to the nearest stars. This was a conceptual leap of almost unimaginable proportions. Aristarchus was suggesting that what appeared to be an enormous cosmos in the Aristotelian model was actually just a tiny local region within a vastly larger universe. But Aristarchus went even further, and this is where his genius becomes almost supernatural in its prescience. He realized that if Earth was moving around the sun, then we should observe stellar parallax, the apparent shifting of star positions as we view them from different points in our orbit. When ancient astronomers couldn't detect this parallax with naked eye observations, most rejected the heliocentric model entirely. The absence of observable parallax seemed to provide definitive proof that Earth couldn't be moving. But Aristarchus made an intellectual leap that wouldn't be vindicated until the invention of powerful telescopes over 2,000 years later. He proposed that the stars were so incredibly distant that the parallax was simply too small to measure with the observational tools available to ancient astronomers. Think about the sheer audacity of this claim. In an era when the fastest anyone had ever traveled was on horseback, and the farthest anyone had ever traveled was to the nearest port seen, clearly was to the horizon a few miles away. Aristarchus was proposing distances so vast that they literally defied human comprehension, suggesting that what appeared to be a cozy, bounded universe was actually an almost incomprehensibly enormous space. He was essentially arguing that the cosmic boundary, if it existed at all, was so far away that it might as well be infinite from any practical human perspective. This was revolutionary thinking that challenged not just the specifics of Aristotelian cosmology, but the very assumption that the universe was scaled to human understanding. The question of cosmic boundaries became even more philosophically complex when ancient thinkers began to seriously consider the nature of infinity itself. The pre-Socratic philosopher Anaximander, writing around 550 BCE, proposed that the cosmos emerged from something he called the apeiron, literally meaning the boundless or the infinite. Anaximander was grappling with a logical problem that still challenges cosmologists today. If the universe has boundaries, what lies beyond those boundaries? If you say, nothing lies beyond, then you're claiming that nothingness has a boundary with something, which seems logically contradictory. How can nothing be bounded by something? If you say, something lies beyond, then you haven't really found the edge of everything, have you? You've just pushed the boundary problem one step further back. Anaximander's solution was radical for its time and remarkably sophisticated in its logical structure. Perhaps the fundamental reality underlying everything was itself infinite and boundless, with our visible cosmos being just a temporary, finite island within an eternal, infinite sea of potentiality. In his model, worlds formed and dissolved within the aporon like bubbles, forming and popping in an infinite ocean. Each individual world, including our own, was finite and had definite boundaries, but the reality that generated these worlds was itself without limits. This allowed Anaximander to have it both ways: cosmic boundaries for the observable world, infinite possibility for ultimate reality. The atomists, led by Democritus around 400 BCE and later systematized by Epicurus, took this reasoning in a direction that sounds remarkably modern to contemporary ears. They proposed that space itself was infinite and filled with an infinite number of atoms moving in an infinite void. In their model, our world was just one of countless worlds scattered throughout infinite space, each one forming through the random collision and combination of atoms, flourishing for a while, and eventually dissolving back into the atomic dance when the atomic arrangements that sustained it became unstable. Epicurus wrote, "There are infinite worlds, both like and unlike this world of ours, anticipating modern concepts of parallel universes and infinite space by over 2,000 years." But here's what's absolutely fascinating about the atomist position. They were proposing that infinity and boundaries could coexist in the same cosmological model. Each individual world, including our own, was finite and bounded. You could, in principle, reach the edge of the Earth, or the edge of the atmosphere, or the edge of the region where our particular atomic configuration dominated. But the space containing all possible worlds was infinite, and the number of atoms available for world building was also infinite, which meant that every possible world that could exist would exist, not just once, but infinitely many times in different regions of infinite space. Sound familiar? This is remarkably similar to our modern understanding of the observable universe as a finite region within potentially infinite space, and it anticipates contemporary ideas about multiple universes and eternal inflation. The atomists also grappled with profound questions about the nature of boundaries that remain relevant to modern physics. If atoms are the fundamental building blocks of reality, what defines the boundary between one object and another? Democritus argued that boundaries are conventional rather than fundamental. A rock ends, and the air begins not because there's some definite line in nature, but because we find it useful to distinguish between regions where rock-type atomic arrangements dominate and regions where air-type atomic arrangements dominate. This insight about the conventional nature of boundaries in a fundamentally atomic reality would later influence everything from Buddhist philosophy to quantum field theory, ancient Chinese. Astronomers approached the boundary problem from yet another angle, developing concepts that were simultaneously more poetic and more philosophically sophisticated than their Western counterparts. The Chinese model of the universe, developed during the Han Dynasty around 200 BCE, described space as infinite but structured, like a cosmic organism with no definite edges, but with natural patterns and rhythms that repeated at different scales. The Chinese astronomers didn't see the need for hard boundaries because they conceived of the universe as a dynamic, ever-changing system where the concept of edge was meaningless, like asking where the edge of a flowing river begins and ends, or where the boundary is between one cloud and another in a constantly changing sky. The Chinese concept of kui, the fundamental energy or substance that fills all of space, provided a framework for understanding cosmic structure without requiring definite boundaries. Qi could condense into visible matter or disperse into invisible potential, but it was never absent from any region of space. This meant that while different regions of the universe might have different densities of qi and different types of organization, there was no location where space simply ended. The Chinese model was thus infinite by default, but it was a structured infinity with patterns and regularities that made it comprehensible and predictable rather than chaotic. Chinese astronomers also developed sophisticated mathematical techniques for dealing with infinite series and recursive patterns that allowed them to model cosmic structures without requiring ultimate boundaries. They were particularly interested in what they called self-similar patterns, structures that looked the same at different scales, like fractals in modern mathematics. This approach to cosmic organization suggested that the universe might be infinite not just in extent, but in complexity, with patterns repeating at smaller and smaller scales, without ever reaching a fundamental level where the pattern stopped. The medieval Islamic astronomers inherited these Greek, atomist, and Chinese traditions and pushed them even further through rigorous mathematical analysis. Scholars like al-Biruni and Ibn al-Haytham in the 11th century began to seriously question whether the Aristotelian model of nested spheres could account for increasingly precise observations of planetary motions. They were particularly troubled by what philosophers call the boundary problem, the logical contradiction in assuming that nothing could exist beyond the boundary of everything. Al-Biruni wrote extensively about this issue, pointing out that if you say there's nothing beyond the outermost celestial sphere, you're still implicitly defining a spatial relationship between the sphere and this nothingness, which suggests that the nothingness must exist in some sense in order to be related to something. Ibn al-Haytham, known in the West as Al-Hazan, approached the boundary problem through what he called critical examination, a precursor to the modern scientific method. He argued that any claim about cosmic boundaries must be testable through observation and mathematical analysis. Since no one had ever observed the edge of the universe, and since the mathematical models that assumed finite boundaries led to logical contradictions, Ibn al-Haytham concluded that the most reasonable hypothesis was that space itself was infinite, with the visible stars marking not a boundary, but simply the limit of human observational capabilities. This was a crucial conceptual leap that wouldn't be fully developed in European astronomy until the Renaissance. Islamic astronomers also made crucial advances in understanding what we would now call coordinate systems and reference frames. They realized that the question of cosmic boundaries might depend on how you choose to describe space itself. Al-Battani in the 9th century developed mathematical techniques for describing stellar positions that didn't require any assumption about ultimate cosmic boundaries. Instead of asking, "Where is the edge of everything?" Islamic astronomers began asking, "How can we describe the positions and motions of celestial objects in the most mathematically elegant and observationally accurate way?" This shift from ontological questions, "What exists?" to methodological questions, "How can we describe what we observe?" was revolutionary and anticipated the approach of modern theoretical physics. But perhaps the most profound ancient insight into the boundary problem came from the Indian mathematician and astronomer Aryabhata. In the 5th century, C.E. Aryabhata proposed that space and time were interconnected in ways that made the question of cosmic boundaries fundamentally unanswerable from within the cosmic system itself. He argued that just as a person walking on the surface of the Earth couldn't determine the Earth's overall shape without somehow leaving the surface entirely, beings within the universe couldn't determine its ultimate boundaries, or lack thereof, without somehow stepping outside the cosmic system itself, which was by definition impossible, since there was no outside to step into. This insight anticipated modern relativistic cosmology by over 1,500 years and highlighted a crucial epistemological problem. How can we study the totality of everything from our position as a small part within that totality? Aryabhata suggested that the boundary problem might be unsolvable not because of limitations in our observational tools or mathematical techniques, but because of the inherent logical structure of the problem itself. If you're inside a system, you can study the internal relationships within that system, but you cannot, even in principle, study the relationship between the system as a whole and anything external to it. Aryabhata's solution was characteristically elegant. Instead of asking whether the universe has boundaries, he focused on developing mathematical models that could describe cosmic phenomena without requiring any assumptions about ultimate limits. His astronomical calculations were based on recursive mathematical relationships that could be extended indefinitely. If the universe turned out to be finite, his equations would still work within that finite domain, and if it turned out to be infinite, his equations could be applied to ever larger scales without modification. This approach of developing boundary-neutral mathematical models would later influence Islamic astronomy and, through Islamic sources, eventually reach medieval European scholars. The ancient puzzle of cosmic boundaries reveals something profound about human nature that remains relevant to our modern scientific enterprise. We are driven to understand the ultimate structure of reality, even when that understanding seems to push beyond the limits of possible knowledge. Every ancient civilization that developed sophisticated astronomy eventually confronted the same fundamental questions. Is space finite or infinite? Does the universe have boundaries? And if so, what lies beyond them? Can something be both bounded and boundless? Are these even meaningful questions? Or do they reflect limitations in human concepts rather than features of reality itself? These weren't just academic questions for ancient thinkers. They were existential challenges that shaped entire worldviews and influenced everything from religious beliefs to political structures to personal ethics. The Babylonian astronomer priests used their cosmic models to justify the divine authority of kings and the eternal stability of social hierarchies. If the universe itself was perfectly ordered with definite boundaries and hierarchical structure, then earthly society should mirror this cosmic order. Greek philosophers used geometric models of the universe to explore the nature of mathematical truth and the relationship between ideal forms and material reality. If the cosmos was constructed according to perfect mathematical principles, then mathematical reasoning could provide access to ultimate truth about the nature of existence. The atomist's infinite cosmos led to a very different set of implications. If there were infinitely many worlds with infinitely many possible arrangements of matter, then every possible life was being lived somewhere. Every possible society was being tried somewhere. And no single way of organizing human affairs could claim cosmic authority. This was philosophically liberating, but also potentially terrifying. If everything possible was actual somewhere in infinite space, then moral choice might seem meaningless, since every action and its opposite were both being performed by infinite copies of yourself in different regions of the infinite cosmos. What's absolutely remarkable about this ancient intellectual struggle is how these thinkers, working without telescopes, without knowledge of other galaxies, without any understanding of the true scale of the cosmos, still manage to identify the core conceptual challenges that continue to perplex modern cosmologists. They recognized that the question of cosmic boundaries is intimately connected to the nature of infinity, the relationship between space and matter, the problem of observation from within the system being observed, the deep philosophical question of whether mathematical models can ever fully capture physical reality, and the fundamental epistemological challenge of studying the totality of existence from a position within that totality. Every single one of these issues remains at the cutting edge of modern cosmological research. Contemporary physicists still debate whether space is finite or infinite, whether the observable universe represents a fundamental boundary or just a limitation of our observational capabilities, whether mathematical models of cosmic structure are discoveries about reality or constructions of human thought, and whether questions about the ultimate nature of the cosmos are scientifically meaningful or philosophically confused. The fact that our ancient predecessors were asking exactly the right questions suggests not only their intellectual brilliance, but also the deep continuity of human curiosity about our place in the cosmic order. And as we'll see in the rest of our cosmic journey today, the observational and theoretical tools we've developed over the past century have revealed that the universe is far stranger, far more beautiful, and far more paradoxical than even the most imaginative ancient philosopher dared to dream. The question of whether an infinite universe can have an edge would have fascinated Aristarchus, puzzled Aristotle, delighted the atomists, and probably inspired Aryabhata to develop entirely new mathematical techniques. We stand on the shoulders of these intellectual giants as we peer into the cosmic abyss, and their questions continue to guide our search for answers at the very edge of human understanding. Fast forward to 1915, and we find ourselves in the middle of one of the most extraordinary intellectual revolutions in human history. While World War I raged across Europe, while empires crumbled and millions died in muddy trenches, a quiet patent clerk turned theoretical physicist in Berlin was about to completely shatter everything humanity thought it knew about space, time, and the very fabric of reality itself. Albert Einstein, working in relative obscurity compared to the titans of experimental physics of his day, was putting the finishing touches on what would become known as the general theory of relativity, a mathematical framework so revolutionary, so counterintuitive, that it would force us to completely reimagine the cosmic boundary problem that had puzzled philosophers for millennia. But here's what makes Einstein's achievement even more remarkable. He wasn't trying to solve cosmological problems at all. He was focused on a much more technical issue. Why did Newton's theory of gravity work so well for most situations, but fail to accurately predict the orbit of Mercury around the Sun? This tiny discrepancy, just 43 arcseconds per century in Mercury's perihelion advance, was the kind of detail that most scientists would have dismissed as experimental error or attributed to unknown perturbing forces. But Einstein had this almost supernatural intuition that small anomalies in well-tested theories often pointed toward fundamental truths about the nature of reality. He suspected that the Mercury problem was telling us something profound about the nature of space and time themselves. What Einstein discovered through years of painstaking mathematical work was that Newton's conception of absolute space and absolute time, the cosmic stage on which all physical processes played out, was fundamentally wrong. Space and time weren't fixed, unchanging backgrounds for physical events. They were dynamic, flexible entities that could be stretched, compressed, twisted, and curved by the presence of matter and energy. Mass literally warped the geometry of space-time around itself, and what we experience as gravitational force is actually objects following the straightest possible paths through this curved space-time geometry. It's like rolling marbles across a stretched rubber sheet with bowling balls placed on it. The marbles don't experience any force pulling them toward the bowling balls, but they follow curved trajectories because the sheet itself is curved. But when Einstein tried to apply his new gravitational theory to the universe as a whole, he discovered something that initially horrified him. The equations of general relativity absolutely refused to describe a static, unchanging cosmos. Every solution to Einstein's field equations for a universe filled with matter showed the same disturbing behavior. Space itself had to be either expanding or contracting. There was no mathematical way to construct a universe that was both filled with matter and permanently static. The cosmos had to be dynamic, evolving, changing over time in its most fundamental structural properties. Einstein was so disturbed by this implication that he made what he would later call the greatest blunder of my life. In 1917, he artificially modified his field equations by adding what he called the cosmological constant, a kind of anti-gravitational force that could, in principle, balance the attractive force of gravity and allow for a static universe. But even this mathematical trick didn't really work. The static universe that resulted from Einstein's modified equations was unstable. Like a pencil balanced on its point, the slightest perturbation would send it either expanding or contracting. Einstein had discovered, almost against his will, that the cosmos must be fundamentally dynamic. Meanwhile, on the other side of the Atlantic, observational astronomers were making discoveries that would soon provide stunning confirmation of Einstein's reluctant theoretical predictions. The early decades of the 20th century were a golden age of telescope construction, with instruments like the 100-inch Hooker telescope at Mount Wilson Observatory pushing the boundaries of what could be observed in the night sky. Astronomers were beginning to study what they called spiral nebulae, mysterious, faint, fuzzy patches of light scattered across the sky that some thought were relatively nearby, clouds of gas and dust within our own Milky Way galaxy, while others suspected they might be entire island universes. Separate galaxies, comparable to our own, but located at enormous distances. The key to resolving this debate came from studying the light spectra of these spiral nebulae. When astronomers passed the light from these objects through spectrographs, they could see the characteristic patterns of absorption lines that indicated which chemical elements were present in the nebulae. But they noticed something puzzling. The absorption lines weren't where they were supposed to be. Instead, they were systematically shifted toward the red end of the spectrum. Red-shifted, as astronomers called it. This redshift could mean only one of two things. Either these nebulae contained exotic forms of matter that absorbed light at different wavelengths than ordinary matter, or the nebulae were moving away from us at tremendous speeds, causing the Doppler effect to stretch the wavelengths of their light. Enter Edwin Hubble, arguably the most important observational astronomer of the 20th century. Working with the Mount Wilson Observatory's powerful telescopes in the 1920s, Hubble embarked on a systematic study of these spiral nebulae that would revolutionize our understanding of the cosmos. First, he definitively proved that the spiral nebulae were indeed separate galaxies far beyond the boundaries of the Milky Way. He did this by identifying individual stars within the nebulae, particularly Cepheid variable stars, whose intrinsic brightness could be calculated from their pulsation periods, and using these standard candles to measure the enormous distances to the nebulae. But Hubble's most shocking discovery came when he plotted the distances of these galaxies against their redshifts. What he found was a clear, linear relationship. The farther away a galaxy was, the faster it was receding from us. This wasn't just a few galaxies showing random motions. It was a systematic pattern that applied to every galaxy he could observe clearly enough to measure both distance and redshift. The implications were staggering. Either the Earth occupied a uniquely special position at the center of a cosmic explosion, with all other galaxies flying away from us specifically, or space itself was expanding uniformly, carrying galaxies along with it, like raisins in a rising loaf of bread. The second interpretation, uniform expansion of space itself, was exactly what Einstein's field equations had predicted, and it resolved the cosmic boundary problem in a completely unexpected way. If space was expanding, then the observable universe had a natural boundary defined not by any physical barrier, but by the finite speed of light and the finite age of the expansion. Light from distant galaxies had been traveling toward us for billions of years, while space itself expanded, creating a kind of cosmic horizon beyond which we simply couldn't see, because there hadn't been enough time since the beginning of the expansion for light to reach us from those regions. But here's where the detective story gets even more fascinating. Hubble's discovery raised as many questions as it answered. If galaxies were flying away from each other like pieces of cosmic shrapnel in the aftermath of a titanic explosion, what was the nature of this explosion? Where did it happen? When did it happen? And most puzzling of all, what was it exploding into? The naive picture of the Big Bang as an explosion of matter into pre-existing empty space led to all sorts of conceptual problems. If the Big Bang happened at a specific location, why don't we see evidence of that special location in the sky? If it was an explosion into empty space, what defined the properties of that space before the explosion occurred? The resolution to these puzzles required yet another conceptual revolution, led by cosmologists like Georges Lemaitre, Alexander Friedman, and later George Gamow. They realized that the Big Bang wasn't an explosion of matter into space. It was an explosion of space itself. There was no pre-existing cosmic arena into which the universe expanded. Space and time themselves came into existence with the Big Bang and have been stretching ever since. This meant that every point in space could claim to be the center of the expansion, because the expansion was happening everywhere simultaneously, rather than radiating outward from a single point. Think about this carefully, because it's one of the most mind-bending concepts in all of physics. When we say space is expanding, we don't mean that galaxies are flying apart through static space like fragments from a conventional explosion. We mean that the distance between any 2 points in space is increasing over time, even if those points aren't moving through space at all. It's like painting dots on a balloon and then inflating the balloon. From the perspective of any dot, all the other dots appear to be moving away, with the farthest dots receding fastest. But no dot is actually moving across the surface of the balloon. The surface itself is stretching, carrying the dots along with it. This revelation completely transformed how cosmologists thought about cosmic boundaries. In the old static universe models, boundaries were geometric properties. You could ask whether space extended infinitely in all directions, or whether it had edges beyond which nothing existed. But in an expanding universe, the boundary question became much more subtle. There were now several different types of boundaries to consider. The boundary of the observable universe, determined by how far light could have traveled since the Big Bang. The boundary of the currently visible universe, determined by which objects we can see right now. And the potential boundary of the actual universe, which might or might not exist, depending on the global geometry of space. The mathematics of expanding spacetime revealed 3 possible geometries for the universe, each with profoundly different implications for cosmic boundaries. If the universe had positive curvature, like the surface of a sphere, but in 3 dimensions, then space would be finite in extent, but without any edges, just like how you can travel around the Earth's surface indefinitely without ever reaching a boundary. In such a universe, if you set off in a straight line and traveled far enough, you would eventually return to your starting point from the opposite direction. The total volume of space would be enormous but finite, and there would be no boundary problem because you could never reach the edge of a spherical space. There simply wouldn't be any edges to reach. If the universe had negative curvature, like a saddle shape but extended to 3 dimensions, then space would be infinite in extent, but would still have the expanding property that Hubble had discovered. In this geometry, often called hyperbolic space, parallel lines diverge from each other, rather than remaining parallel as they do in flat space. And the angles of triangles add up to less than 180 degrees. A negatively curved universe would be infinite and would have no boundaries anywhere. But different regions of this infinite space would be expanding away from each other, creating the redshift pattern that Hubble observed. The third possibility was that the universe had 0 curvature, perfectly flat space like the familiar Euclidean geometry we learn in school, but extended infinitely in all directions and expanding uniformly. In flat space, parallel lines remain parallel. The angles of triangles add up to exactly 180 degrees, and the ratio of a circle's circumference to its diameter is exactly pi. A flat universe could be either finite or infinite depending on its topology. Roughly speaking, how the flat space was connected to itself. You could have an infinite flat universe that extended forever in all directions, or you could have a finite flat universe that wrapped around on itself like a cosmic donut or Klein bottle. Determining which of these 3 geometries described our actual universe became one of the holy grails of observational cosmology. The curvature of space could, in principle, be measured by carefully studying the relationship between distance and redshift for very distant galaxies, or by measuring the apparent sizes of objects at different cosmic distances, or by analyzing the statistical properties of temperature fluctuations in the cosmic microwave background radiation. Each approach required pushing observational technology to its absolute limits and developing increasingly sophisticated theoretical models to interpret the data. The breakthrough came in the late 20th and early 21st centuries, with space-based observatories specifically designed to study cosmic microwave background radiation, the afterglow of the Big Bang itself. The Cosmic Background Explorer, COBE, satellite in the 1990s, followed by the Wilkinson Microwave Anisotropy Probe, WMAP, in the 2000s, and then the European Planck satellite in the 2010s, made incredibly precise measurements of tiny temperature variations in this primordial radiation. These temperature fluctuations, imprinted on the cosmic microwave background when the universe was only about 380,000 years old, carried information about the geometry of space itself. The verdict from these cosmic microwave background studies was stunning. Our universe appears to be almost perfectly flat. The curvature is so close to zero that even with our most sensitive measurements, we cannot detect any deviation from perfect flatness. This discovery had profound implications for the cosmic boundary problem. In a flat universe, if space extends infinitely in all directions, then there are no boundaries anywhere. You could travel forever in any direction and never reach an edge. But the flatness of space doesn't tell us whether the universe is actually infinite or whether it might be finite, but wrapped around on itself in some complex topological configuration. The flatness discovery also connected cosmology to one of the deepest problems in theoretical physics, the fine-tuning problem. For the universe to be as close to perfectly flat as we observe, the initial conditions at the Big Bang had to be tuned to incredible precision. Roughly 1 part in 10 to the power of 60. Any significant deviation from perfect flatness in the early universe would have been amplified by cosmic expansion, leading to a universe that either collapsed back on itself within microseconds, if it started with positive curvature, or expanded so rapidly that matter could never clump together to form galaxies and stars, if it started with negative curvature. The fact that we exist in a universe that's flat enough for structure formation to occur, but not so flat that it's completely homogeneous, represents one of the most remarkable fine-tunings in all of physics. This fine-tuning problem led cosmologists to develop the theory of cosmic inflation, the idea that the very early universe underwent a period of exponentially rapid expansion that stretched space so dramatically that any initial curvature was flattened out, just like how a small patch of a balloon's surface appears flat if you blow the balloon up to enormous size. Inflationary cosmology provided a natural explanation for why space appears flat today, but it also raised new questions about cosmic boundaries. If inflation could flatten space to the degree we observe, it might also have stretched the universe to sizes far larger than the observable universe, potentially making it infinite even if it started out finite. The inflationary scenario also suggested that our observable universe might be just one tiny patch within a vastly larger multiverse, a potentially infinite collection of causally disconnected regions, each with its own physical properties and evolutionary history. In this picture, what we call the universe would be like a single bubble in an infinite ocean of space-time foam, with our cosmic horizon marking not the edge of everything that exists, but merely the boundary of the region we can observe from our particular location in the multiverse. Modern cosmological observations have thus transformed the ancient boundary problem in ways that would have astonished even the most imaginative classical philosophers. Rather than asking whether the universe has a single, definite edge beyond which nothing exists, we now recognize multiple types of boundaries. Observational boundaries, defined by the finite speed of light and the finite age of cosmic expansion. Physical boundaries that might exist due to the large-scale topology of space, and causal boundaries that separate different regions of an inflationary multiverse. Each type of boundary has different properties and different implications for our understanding of reality. The detective story of modern cosmology reveals that the universe is far stranger and far more subtle than our ancestors could have imagined. Space itself can expand, contract, and curve in response to the matter and energy it contains. Time itself had a beginning with the Big Bang and flows differently in regions with different gravitational fields. The boundary between inside and outside the universe becomes meaningless when space and time themselves are dynamical entities that can be created, destroyed, and transformed. We live not in a static cosmic container, but in a dynamic, evolving spacetime whose properties we're still working to understand. And yet, for all our sophisticated theoretical frameworks and precision observational techniques, we still face versions of the same fundamental questions that puzzled ancient philosophers. Is the totality of physical reality finite or infinite? Are there regions of existence that are in principle unobservable to us? Can we meaningfully discuss the boundary of everything that exists? Or does the very concept of a cosmic boundary reflect limitations in human thought rather than features of objective reality? The tools we've developed to address these questions are incomparably more powerful than anything available to ancient astronomers. But the questions themselves retain their profound philosophical depth and their power to inspire wonder about our place in the cosmic order. As we'll see in the next part of our journey, the modern synthesis of general relativity, quantum mechanics, and observational cosmology has led us to a remarkable conclusion about the relationship between cosmic boundaries and infinite space. One that would have delighted some ancient philosophers while completely confounding others, and one that continues to challenge our deepest intuitions about the nature of existence itself. Let's pause and contemplate one of the most mysterious and mind-bending divides in all of cosmology, the boundary between the observable universe, the entirety of what humanity can potentially see, measure, and study, and the actual universe, the unfathomable vastness that exists far beyond our observational reach. This is territory where physics, philosophy, and existential curiosity all meet, and where ancient wonder merges with cutting-edge astrophysics to fuel some of our deepest questions. The observable universe is a scientific construct, a sphere centered on us, Earth, and defined not by walls of matter, but by the relentless march of time, the immutable law of the speed of light, and the cosmic history written across billions of years. It is a moving front, advancing as the universe matures, framing everything our telescopes and detectors could possibly record since the primordial fireball of the Big Bang. Yet this is only a sliver of reality. Beyond this shimmering edge, beyond the distant curtain of time, may lie realms so vast, so profoundly alien in their contents and structure, that our words, concepts, and mathematics can only gesture at them, spaces where the most fundamental limits of knowledge become tangible. The definition and nature of the observable universe. First, let's decipher what astronomers mean by observable universe. It's easy to think the universe we see is all the universe there is, but physics teaches us this is an illusion. The observable universe is the region of space from which light and other messengers, gravitational waves, cosmic rays, have had time to reach us since the cosmic dawn. Given that light travels at a finite speed, and the universe is 13.8 billion years old, this sphere's radius is not simply 13.8 billion light years. Because the universe expands, the horizon is actually much larger, about 46 billion light years in any direction from Earth. The diameter, a staggering 93 billion light years across, a boundary that envelops around 2 trillion galaxies, hundreds of billions of stars per galaxy, and, quite possibly, trillions of planets. But here's the twist. This edge isn't an edge of physical stuff, nor is it universally the same for everyone. It's not a cosmic wall, a glittering shell, or a force field that stops exploration. The true edge of the observable universe is defined by past light cones, the path that light and other signals have taken to reach Earth. These cones stretch outward through expanding space, marking the limits of what has been visible up to now. Every observer, anywhere in the universe, has their own observable bubble centered on them. If you travel to a galaxy 5 billion light years away from Earth, your new horizon shifts accordingly, and you can see light that Earth-bound astronomers will never receive. The edge, therefore, is not absolute but personal, a local feature, not a universal one. Why do we have an edge at all? This brings us to the great cosmic detective puzzle. Why is there this edge? Why isn't the whole cosmos equally visible to all observers, regardless of distance or motion? The answer lies in the foundational properties of our universe, its finite age and the finite speed of light. When the universe began in a super hot, dense state, the Big Bang, the whole cosmos was opaque for its first 380,000 years. Photons, the particles of light, couldn't travel far before being absorbed and scattered by the plasma of charged particles that filled the young universe. Only when atoms formed in the event called recombination did the universe become transparent, allowing light to escape and race across the expanding voids. This primeval glow, the cosmic microwave background, CMB, marks the earliest visible surface of the universe. The CMB surrounds us in every direction, painted on the inside of our observable sphere like an ancient cosmic fresco, its patterns encoding the universe's geometry, composition, and origins. From this moment onward, the edge of our observable universe was set not by material boundaries, but by time itself. Light travels at 299,792 kilometers per second, but no signal can exceed it, and signals emitted just after recombination have only reached so far. Billions of years later, the universe has expanded incredibly, stretching the initial burst of photons into microwaves and making our cosmic horizon ever larger. The further we look, the further back in time we see. Looking at the galaxy, whose light left it 10 billion years ago, we witness its ancient youth, its primeval glow. Yet, there's always a limit, a horizon, beyond which no signal has reached us. Our technology, no matter how advanced, is fundamentally limited by the speed of light and cosmic age. It's a barrier of knowledge, not matter. Beyond it, the universe remains dark, unobservable, and perhaps forever unknowable. The expanding universe and moving horizons. But cosmic expansion means the story gets even stranger. As the universe grows, the distances between galaxies stretch, so the photons we observe today have traveled a far longer journey than their initial emission distance. Galaxies, whose light originated 13.8 billion years ago, are currently about 46 billion light years away and getting farther every second. Expansion means that our horizon increases, not because the universe is aging, but because space itself is stretching. And as a cosmic twist, there are galaxies so distant that although their photons are traveling toward us, they are also being carried away by the expansion of space so fast that their light may never reach us. Not now, not in the future, not ever. These galaxies exist beyond the cosmic event horizon, a boundary of future observability set by the expansion rate. In our accelerating universe, driven by dark energy, regions recede so fast that even light cannot bridge the distance. But inside our horizon, the expanding universe has drawn a line, marking all that's ever possible to observe. Each observer draws their own sphere, a patchwork mosaic of perspectives layered over the cosmic fabric. The actual universe, beyond the observable bubble. If all this is true for the observable universe, what lies beyond? Here, science veers away from direct measurement and plunges into theory, inference, and awe. The actual universe is the total cosmic expanse, whether finite or infinite, whether similar to our region or alien in unimaginable ways. It is the sum of all that is, not just all that can be seen. If the universe is infinite, and current evidence gives us reason to think so, then our observable patch is just one droplet in an infinite ocean. Beyond our horizon are countless more galaxies, stars, planets, and perhaps even entire cosmic structures, each as real and material as our own, but eternally beyond reach. If the actual universe is finite, its true size may still be vastly bigger than what we observe. The cosmic horizon could simply be a barrier beyond which our knowledge cannot venture, not a wall enclosing reality itself. Modern cosmology suggests no edge or boundary in the classical sense. Space might be infinite, or it might be finite but unbounded, looping back on itself like the surface of a sphere or torus in higher dimensions. Observable versus actual, philosophical and physical implications. Why does this distinction matter so deeply to science and philosophy? Because it forces us to grapple with both hope and humility. Our observable universe is, in some sense, the biggest laboratory and archive of cosmic history available to humanity. We use its light to reconstruct stellar evolution, galaxy formation, the rise and fall of cosmic structures, and to measure fundamental constants that shape all existence. We can even test the most arcane theories about time, matter, and energy. But recognizing its limits imposes profound humility. The edge we see is not the edge of all that exists, just the edge of what is knowable from Earth or from any position in the cosmos. Any claim about the universe must be rooted in understanding this boundary, and any leap of theory beyond it must be made in full awareness that the unobservable is always beyond verification. The observable actual divide brings fresh urgency to old philosophical puzzles. If our horizon marks all that is knowable, what do we say about what lies beyond? Is it meaningful to theorize about realms that no observation can ever touch? Are the laws of physics the same beyond our horizon? Do galaxies recede forever? Do stars shine with familiar spectra? Do particles behave just as they do here? Or could the universe out there be fundamentally different, beginning perhaps with different symmetry, forces, or structure? Some theorists even speculate about cosmic regions where the laws of physics themselves vary, like bubbles in a multiversal foam. If inflationary models of the early universe are correct, our observable patch may be one of countless domains with their own physics, their own populations, maybe even their own versions of life. Cosmic homogeneity is what's out there, like what's in here. One of cosmology's most beautiful and rigorous assumptions is the cosmological principle. On large scales, the universe is both homogeneous and isotropic, meaning it looks the same everywhere, in every direction. This principle lets cosmologists infer that what we see in our horizon, a broad distribution of galaxies, dark matter filaments, cosmic voids, is not a local accident, but a universal pattern. But here, empirical rigor meets conceptual challenge. We cannot see beyond the cosmic horizon. If the universe is truly infinite, then the arrangement of atoms, galaxies, and perhaps even events repeats endlessly, lending credence to the wild idea that every possibility happens somewhere. Another Earth, another you, another night sky, with subtle differences. In an infinite cosmos filled with matter and energy, statistics declare that everything possible occurs, not once, but infinitely many times. If, instead, the universe is finite but unbounded, then these repetitions are rare, and the complexity of reality is more constrained, still incomprehensibly vast, but not infinite. The role of measurement. How do we know? How do cosmologists probe the edge and reach these conclusions? By using light as both messenger and clock, by measuring redshift, the stretching of wavelengths caused by cosmic expansion, which lets observatories chart the ancient galaxies, map distances, and calculate the universe's geometry. Observations of the cosmic microwave background detect minute variations and patterns that reveal not just the size of the observable universe, but the curvature of spacetime itself. These measurements confirm that the observable universe is overwhelmingly flat, meaning Euclidean geometry holds true on vast scales, and there's no sign the cosmos is curled back on itself. But flatness is consistent with both infinity and vast finitude, so the true span of the actual universe remains elusive. And as technology evolves, astronomers search for signatures through gravitational waves, neutrinos, or perhaps space-time anomalies that might let us glimpse hints of what lies beyond the observable horizon. A personal universe, every point has its horizon. Perhaps the most surprising result of all is this: the observable universe isn't centered on Earth out of cosmic favoritism. Every galaxy, every planet, every grain of cosmic dust has its own observable region, its own unique bubble centered at its location. There's no preferred center in the actual universe, no cosmic throne where the laws of physics are anchored. Instead, every spot in the universe has its private horizon, its slice of observable reality, and its unknowable beyond. As an observer on Earth, you reside inside a sphere with a 46 billion light-year radius. For an alien in Andromeda, or some galaxy halfway across the universe, their bubble is centered on them. Your observable universes overlap, but each is unique. What lies beyond one edge is visible within another's, and vice versa. If all observers' data could be combined, the composite picture would stretch ever farther, but always remain bounded by the edge of light, time, and expansion. Cosmic fate. Will the horizon always exist? Given expansion and the presence of dark energy, a mysterious force driving acceleration, our observable universe is actually shrinking in a cosmic sense. As galaxies recede faster and faster, vast regions of space slip permanently beyond our reach. The further into the future, the less we will ever see. Astronomers today may thus enjoy the richest cosmic horizon that will ever be available to any civilization on Earth. In trillions of years, only galaxies bound by gravity to our own will remain visible. In cosmic terms, everything else will have disappeared beyond forever. It's a bittersweet revelation. The observable universe isn't static. Its boundary moves as time ticks forward, but its effective contents will slowly dwindle. Our current cosmic map is the most complete ever, and future generations will see ever less. Not because the actual universe shrinks, but because the edge races ahead faster than signals can reach it. Science, philosophy, and the quest for meaning. The distinction between observable and actual universe adds a powerful layer of meaning and humility to science. Recognizing the limits of our knowledge doesn't shrink our ambitions. It sharpens our wonder. Modern cosmology, grounded in mathematics and physical law, is a celebration of what can be known and a continual challenge to push those boundaries wider. But every new discovery, each distant quasar, each flicker of the early universe detected in microwave background, also reminds us that reality infinitely exceeds the map we can draw. Our instruments, no matter how refined, rise against the cosmic darkness, illuminating a finite region. That region may be expanding in reach, but the actual universe remains open-ended, possibly infinite, beyond our ability to ever exhaust its contents. And this is not a failing of science. It's an invitation to awe, a call to humility, and a responsibility to study, contemplate, and respect the edge between knowledge and mystery. The ultimate paradox: infinite universe, finite knowledge. So let's sum up the paradox that anchors the heart of modern cosmology. We live in a universe whose true scope may be infinite, but we can always only ever know a finite portion of it. The observable universe is defined by light, time, expansion, and geometry, a boundary painted by the speed of photons and the age of everything. Beyond it, the actual universe stretches deeper, perhaps endlessly, filled with galaxies, worlds, and possibilities we can never touch. The horizon we see is not a limit on existence, but on knowledge, a line drawn by the universe itself, shaping what science can, in principle, observe. And for the curious, those who wonder, or those who dream on a clear, starry night, the cosmos offers both comfort and challenge. In its structure, the edge is ever present, marking the boundary between the known and the unknowable. Yet in its vastness, it reminds us that beyond every edge is perhaps an infinity of realities, waiting not for our telescopes, but for our imagination. The observable universe is our playground and our lab. The actual universe is our mythic frontier. The line between them, drawn not by walls, but by the rules of physics, is the prompt, the page, and the perpetual source for all our greatest questions. And that is why, when you look at the stars and ask, how far does this go? You're part of a cosmic tradition, forever questing, forever searching, at the edge of everything. What does it truly mean for the universe to be infinite and yet have an edge? If you've followed our journey so far through the ancient puzzles, the cosmic detective story, and the mysterious divide between the observable and actual universe, You may feel the paradox closing in. It's a challenge to the deepest intuitions, an intellectual knot that's left generations of philosophers, priests, mathematicians, and physicists both awestruck and obsessed. How can something go on forever and yet still admit some kind of boundary? Let's unravel this paradox step by step. With the same determination as Einstein modeling spacetime, with as much humility as an astronomer peering into a telescope, and with the insatiable curiosity of humanity itself. Edge versus infinity. The language of boundaries. Before exploring cosmic specifics, it's crucial to clarify the ideas and language we use. Throughout history, edge has meant different things. It can be a physical boundary, like the surface of the Earth or the rim of a bowl. Or it might be a conceptual boundary, as when we talk of the limits of human perception, measurement, or comprehension. Infinity, meanwhile, isn't just a big number. It's a concept that stretches past every finite figure you can name, past every imaginable distance or quantity. So when cosmologists speak of the universe lacking an edge, but possibly being infinite, they're touching on one of the deepest logical and philosophical problems imaginable. Can geometry, measurement, and even existence itself truly run out? Or are such boundaries always artifacts of our perspective and tools? To resolve the paradox in the context of cosmology, we need both rigorous science and flexible thinking. We must learn to distinguish between the edge of what we observe and the structure of all that exists, and to accept that these questions are not just semantic, they're physically meaningful. Beach balls, flat sheets, and cosmic geometry. Let's use some classic thought experiments and analogies drawn from both physics and everyday experience. Consider the surface of a beach ball. If you're a tiny creature living in 2 dimensions, walking the surface of that ball, you'd never encounter an edge. Your world would be unbounded. You could travel forever and never reach a wall. Yet the surface itself is finite. It has a calculable area, and it loops back on itself. This is a classic example of finite but unbounded geometry. Modern cosmology allows that the universe in 3 dimensions could be similar. Finite in overall size, yet with no edge anywhere. Contrast this with a flat sheet of paper. If it's infinite, you can walk endlessly and never encounter an edge. Space just stretches on, and on, and on. But what if you cut the sheet somewhere? Then you've given it an edge, a clear boundary that marks where the sheet ends and empty space begins. Now, bring these analogies into cosmic science. The universe, as best as we can measure, appears to be flat, not curved like a sphere, meaning the rules of Euclidean geometry hold true at very large scales. This doesn't automatically mean infinity. There can be a flat but finite universe if space is wrapped in higher dimensions, or an infinite flat universe expanding forever. The modern mystery is this: if the universe is infinite and flat, does it have an edge? Or does edge require a finite structure, and is everything beyond that simply more universe? The paradox arises not in the math, but in our attempts to wrap intuition around infinity. Einstein's relativity and the end of edges. Einstein's general theory of relativity changed everything. Rather than seeing space as static and absolute, relativity made it clear that space-time is dynamic. It can expand, contract, curve, ripple, and even connect in higher dimensional ways. General relativity admits spacetimes that are finite, infinite, bounded, or unbounded, sometimes all at once, depending on what properties you study. If the universe is closed, it's finite, but without an edge. Every path loops around seamlessly. If it's open or flat and infinite, space stretches on endlessly, no edge in sight. But relativity also suggests that observation itself is limited. Light travels at a finite speed, and the universe is a finite age. So the edge of the observable universe isn't an edge in reality, but a limit of perception. Beyond that, the cosmos may be similar or wildly different. Einstein showed that edges are often features of reference and measurement, not of space itself. Observable universe, our apparent boundary. Let's focus on the observable universe, a well-defined, measurable region. For any observer, the universe appears as a sphere centered on their position, stretching about 46 billion light-years in all directions. This isn't a natural wall, but a cosmic horizon, the maximum distance from which light has had time to reach us since the beginning of the universe. But what lies beyond? Most likely, there is more universe, galaxies, stars, cosmic structures, gas, dark matter, more cosmic expansion. Yet these objects are forever outside our reach. Their signals haven't arrived, and potentially never will, due to the accelerating cosmic expansion driven by dark energy. So the paradox sharpens. We see a sphere, an edge, yet know, from theory and from the evidence of cosmic flatness and homogeneity, that this edge is only apparent. Science tells us the universe continues beyond, potentially forever. Each observer, anywhere in space, defines their own observable sphere. The actual universe is much larger, or infinite. The false edge, boundaries of knowledge, not reality. The edge of the observable universe is thus a barrier not of being, but of knowing. It's defined by how far light has traveled, not by a property of the universe itself. This is the horizon problem, the realization that our cosmic map is always incomplete, bounded by the rules of relativity and the finite speed of light. Consider the analogy of standing on the ocean's shore. The horizon seems like an edge, a place where sky meets water, a boundary of vision. But if you sail out, the horizon moves with you, revealing more ocean. The edge is always local, personal, and moves as you move. So too with the universe. Every point in the universe, every star, planet, alien civilization, has its own cosmic horizon, its own observable sphere. All these horizons overlap, each marking a personal boundary, never an absolute one. Finite but unbounded, curved space. Some geometries permit the universe to be finite but lack an edge. The most familiar is the surface of a sphere. Move in any direction long enough, and you return to your starting point, but never encounter a boundary. In 3 dimensions, this is a closed, curved universe, a possibility allowed by Einstein's equations. If the real universe is a 3-dimensional hypersphere, then it's finite in volume, but contains no wall, no edge. You could travel forever and always loop back. This is how physicists resolve the ancient paradox about what lies beyond the edge. There is simply no beyond. Current measurements of cosmic background radiation indicate that, if such curvature exists, it's extremely slight, far less than we can presently detect. Most data points toward a flat universe, but allows for gentle curvature that may or may not result in a true finite cosmic volume. Infinite flat universe, edge-free infinity. The universe may be both flat and infinite. In this scenario, there is no limit, not even a subtle curve. Space extends endlessly, with no boundary anywhere. This means that our cosmic horizon is just a tiny bubble in an immense, endless sea. The edge is not part of reality, nor even required. The universe truly does go on forever, filled with endless stars, galaxies, and perhaps planets, each with their own horizon, each forever expanding as the universe ages. Here, the paradox is sharper still. The infinite makes sense in equations, but defies visualization. Just as there is no largest number, there is no end to an infinite universe. Its size cannot be measured or imagined. Its extent renders every region small by comparison. The Big Bang, everywhere, no center, no boundary. The Big Bang is often misunderstood as an explosion at a particular place in pre-existing space, hurling matter outward into emptiness. But in reality, it was the creation and continuous stretching of space itself. The expansion happened everywhere at once. There was no center of the explosion, no edge where it began or ends. As such, every point in the universe is equally valid, and the universe's expansion means new space is being created everywhere. This resolves another ancient worry. If the universe started at one point, why do we seem to be at the center? The answer is, everyone is at the center of their observable universe, and expansion is happening everywhere. Cosmic homogeneity and repetition, the infinite implications. If the universe is truly infinite and filled with galaxies, then something mind-bending emerges. In such immensity, every possible arrangement of matter must not only occur, but repeat endlessly. There's a place, hugely remote, where the arrangement of atoms matches that of your room, of Earth, of the whole solar system, simply because infinity doesn't run out of combinations. There could be infinite copies of our planet, our galaxy, or even you, each living out every possible history that physics permits. This is the mathematical consequence of infinite size and statistical variation. Such implications are dizzying, moving from science to philosophy, and even to questions of identity and existence. If everything possible happens somewhere, what separates us from those distant copies? Is our sense of uniqueness only local? In the actual infinite, are we alone or just one of infinitely many? The event horizon, the edge that escapes forever. Our observable universe also has a second kind of edge, the event horizon. As the universe expands faster and faster due to dark energy, there are regions of space from which signals sent today will never reach us, no matter how long we wait. This event horizon is a dynamic boundary, marking the cosmic regions lost to us due to expansion. In the far future, ever more galaxies and structures will slip past this horizon, disappearing from view forever. This means that the observable universe is not just finite now. It shrinks in practical terms with time. Cosmic data will fade, and only the nearest galaxies, those gravitationally bound to us, will remain visible. In the remote future, the cosmic web of galaxies will dissolve past view, leaving a lonely island of stars in perpetual darkness, an edge imposed not by existence, but by cosmic fate. No absolute edge. Every observer has their horizon. One of the most profound realizations in modern cosmology is that cosmic boundaries are not universal. Every position in the universe, every observer, human, alien, or hypothetical, sees their own horizon, their own edge. There's no cosmic center, no privileged spot. Each sphere overlaps with others, but none represents the true edge. This decentralization upends every ancient cosmic model, from Aristotle's Earth-centered spheres to modern science fiction visions of walls at the universe's edge. There is only the physics of relativity, the expansion of space, and the local horizon dictated by the rules of light and time. Are boundaries real? Throughout science, the concept of a boundary has evolved. In particle physics, there is no wall between atoms, just regions where the probability of quantum events changes. In the mathematics of infinity, boundaries are artifacts of definition, not objects in themselves. For the universe, edges are meaningful only with respect to an observer, either as limits of knowledge or regions of highest probability. Reality doesn't have walls. It has local limits. The actual infinite universe doesn't need an edge. Topology and higher dimensions, strange spaces without edges. Modern mathematics allows for even stranger resolutions to the paradox. Spaces that are finite, have no edge, and possess a topology so alien it defies everyday intuition. Consider the torus, the donut shape. If space were toroidal, traveling far enough in one direction would bring you back to your origin, with no edge anywhere. Higher dimensional structures, Klein bottles, spheres, n-dimensional surfaces, could allow reality to be finite but utterly unbounded. These models resolve the paradox in math, but the question remains whether physical reality matches these mathematical constructs. So far, cosmic background measurements tell us the universe is flat, but leave room for subtle topology we've yet to glimpse. The power and limit of scientific inference. How do scientists infer the existence or non-existence of edges? They use cosmic microwave background radiation, the distribution of galaxies, gravitational wave echoes, patterns in large-scale structure, and deep theoretical models. All data so far point to homogeneity and flatness, an edge-free cosmos. But there's a limit. Since we cannot observe beyond our horizon, inferences about the universe as a whole are necessarily inductive, not deductive. We extrapolate from known physics and local observations, but cannot be certain. The actual universe may contain surprises, regions beyond our grasp. The paradox, forever facing the infinite. The paradox, ultimately, is lived by every curious mind. We peer out at a measurable universe, defined by light, time, expansion, and gravity, and encounter an edge, a spherical horizon past which our signals and our questions cannot go. Yet every theory, every equation, every extrapolation tells us the cosmos stretches further, perhaps endlessly. Our edge is a shroud of ignorance, not of existence, a local boundary drawn by physics, not by walls. The universe is infinite, possibly, but our insight is forever finite. In this way, we inhabit a universe that is at once boundless and bounded, boundless in its structure, bounded in our knowledge. Implications for human understanding. What does resolving this paradox mean? It means embracing humility. No matter the power of our telescopes, the brilliance of our mathematics, or the depth of our imagination, we are always limited by perspective. The edge of knowledge is not the edge of reality. It means honoring even more deeply the privilege of being conscious, curious observers. Our cosmic horizon, though finite, contains almost all the evidence needed to decode the history of stars, galaxies, chemistry, and life. The edge taunts us, but also grants us the space to explore, and it means recognizing the beauty of the paradox, living at the intersection of the infinite and the finite, forever seeking answers at the edge of possibility. Beyond science, the philosophical edge. The edge also calls for philosophical humility. What can be known? What exists? What is real? These questions, sharpened by cosmic discovery, lead us to the oldest debates in philosophy. Is reality defined only by what is observable? Or can we speak meaningfully about what lies beyond? Quantum mechanics tells us that unobserved particles exist in a liminal state of probability. Cosmology teaches that unobserved regions persist, but are forever beyond reach. Our lives, our very meaning, are shaped by the lines we draw between what is accessible and what is not. The paradox is not just of infinite space and apparent boundaries. It's of the human quest to know and the acceptance of limits. The paradox revealed synthesis. So, can the universe be infinite and still have an edge? The answer, in the language of cosmology, is both yes and no. The observable universe, the edge you can measure, study, map, exists, but is merely the frontier of knowledge, not the frontier of everything. The actual universe, whether infinite or finite but unbounded, contains no wall, no final curtain. It stretches far beyond every local horizon. Every ancient model of boundaries, every myth, every mathematical proof, finds resolution in modern cosmology. The edge is only a placeholder for uncertainty, infinity for possibility. Humanity stands, forever, at both, the edge of all that we know, and the threshold of everything yet to be learned. As you reflect on this paradox, remember, the greatest scientific stories begin not with answers, but with the tension between what is known and unknown. At the interface of edge and infinity, we find the true heart of scientific adventure, curiosity that never quits, questions that never end, and a universe that always, always has more to reveal. Outro paradox. The paradox has not just been revealed, but embraced. By seeking the edge, we touch the infinite. By studying the known, we honor the mystery of all that lies beyond. In the cosmic ocean, every horizon is a beginning, every boundary a dare, and the infinite stretches before us, forever teasing, forever welcoming, forever unknown. Imagine, for a moment, loosening the grip of everyday intuition. Shed the familiar and prepare to stare fully into the cosmic abyss, the place where the notions of infinity, edge, repetition, possibility, and destiny converge. This is the terrain of mind-bending implications, the fascinating consequences that arise when we truly accept what science tells us about space, time, and the universe's deepest structure. Let's begin by recapping what we hold to be true so far. The universe may be infinite, extending beyond every possible visual or physical horizon. There may be no edge, no wall, not even a boundary of emptiness. The observable universe is just a tiny drop in an endless ocean that stretches in all directions, forever. And within our patch of space, the laws of physics hold, stars shine, galaxies swirl, and life emerges. But what does this mean? Not just scientifically, but philosophically. What are the far-reaching, sometimes unsettling, and always astonishing conclusions that flow from our best theories? 1. Infinite copies and the ultimate repetition. In an infinite universe with finite arrangements of matter, statistics dictate something extraordinary. Every physically possible configuration of matter must recur, not just once, but endlessly. This isn't science fiction, but straightforward mathematics born from the ergodic hypothesis. If atoms can organize themselves in a trillion ways, and an infinite universe provides infinite opportunities, every possible arrangement occurs. Somewhere out there, untold light years beyond your cosmic horizon, there's a region where the arrangement of stars, galaxies, and atoms perfectly matches your own room, down to the placement of dust grains, the flicker of your screen, and even the thoughts in your mind. There is a copy of you, or a near copy, or a million subtle variations. You, with a different shirt, a different meal, speaking a different word, or deciding to pause this video and take a walk instead. Think about the statistical consequences. If the number of possible configurations in a region the size of Earth is, say, 10 to the power of 10 to the power of 50 to the power of 10 to the power of 10 to the power of 50, then an infinite universe guarantees that every such configuration happens not once, but countlessly, scattered through the infinity of space. This idea explodes the boundaries of identity and uniqueness. Are you one among many, or infinitely duplicated? Does choice matter if every outcome plays out somewhere? Is the self a property of place or repeated circumstance? For some, this is comforting, a kind of cosmic immortality. For others, it's disquieting. Yet the mathematics is relentless. Infinity requires repetition. The cosmos becomes not just the source of stories, but the infinite library of all stories. 2. The principle of mediocrity. We are not the center. The Copernican principle, sometimes called the principle of mediocrity, states that we are not at a special place. The universe does not revolve around Earth. The laws of physics hold everywhere, and our vantage is not unique. But if the universe is infinite, the implications go further. Not only is Earth not at the center, every place is indistinguishable from every other on large enough scales. The universe is homogeneous and isotropic. The same physics applies in every direction. No galaxy, solar system, or person is at a privileged position. Philosophically, this flattens our cosmic importance. Religion and mythology often put humanity at the universe's heart. Science, by uncovering infinity, gently but powerfully undermines anthropocentric thinking. And if sameness truly reigns at scale, then the lessons learned here about molecules, planetary systems, evolution, and even civilization may echo everywhere. What we learn is, simultaneously, particular and universally resonant. 3. The Big Bang, expansion, everywhere, and the loss of a center. Science popularization often gets this one crucial idea wrong. The Big Bang was not an explosion at a place, but an expansion of space itself, happening everywhere at once. There is no center, no cosmic origin you can point to on a map. Every spot is as central as any other. The fabric of space itself is stretching. Galaxies recede because the distances between them increase. This reframes the meaning of edge. There is no edge out there. The process happens everywhere. And this complicates our intuitions about time, destiny, and causality. If the universe had a beginning but no center, then where and when ends become meaningless. Time itself began with the Big Bang. There was no before. Likewise, there is no outside to the universe, no abandoned shell or empty abyss. This contradiction between our spatial intuitions and time's physical structure challenges everyday reasoning and invites a profound humility. We are creatures within space and time, not observers outside. 4. The multiverse hypothesis, more than one universe. Inflationary cosmology and some interpretations of string theory suggest that our universe, vast as it is, may be just one bubble in a fizzy, ever-expanding cosmic ocean called the multiverse. Other universes, with different physical laws, different constants, and different cosmic histories, may exist. Inflation can cause pocket universes, bubbles, to arise, each expanding at its own rate, each its own cosmos. If so, even infinity within our universe is just a narrow slice. The totality of existence may be infinitely larger still, with infinite causal domains, each with their own observable edges. This means that human physics, the rules we deduce by experiment, may apply only locally. Constants may vary elsewhere. There could be universes where gravity is stronger, matter is made of different particles, or time runs at a different pace. The implications? Knowledge itself becomes local, contextual, provisional. Science is universal within our horizon, but the multiverse places the largest imaginable question mark over notions of absolute truth. The arrow of time and the mystery of entropy, the universe's expansion, doesn't merely affect distance, it shapes the arrow of time in the increase of entropy. The second law of thermodynamics tells us entropy increases, disorder grows, complexity erodes, and time's arrow moves forward. In an infinite universe, this plays out on unimaginable scales. Stars burn out, galaxies disperse, black holes evaporate, and complexity gradually turns to cosmic dusk. But with endless regions, each evolving on its own clock, each with its own cosmic fate, there may be domains where entropy runs differently, or where local arrows of time diverge. This inspires both a cosmic melancholy and a vibrant sense of possibility, the ultimate fate, heat death, or, in some models, the spontaneous fluctuation of new low-entropy regions, birthing new universes, new histories. Time, in the cosmic view, is both tragedy and possibility, a never-ending stage for the birth and death of worlds. 6. Destiny and the future of observation. If, as observations suggest, cosmic expansion is accelerating due to dark energy, our own cosmic horizon is shrinking in future terms. Eventually, only the nearest galaxies, those gravitationally bound to ours, will remain visible. The rest will fade past the event horizon, never to be seen or contacted again. Civilizations of the far future, no matter how advanced, will be confined to a seemingly empty island universe. Our vantage point is, in some sense, at the cosmic peak. Future observers will have less data, less evidence, less cosmic connection. This singular moment in cosmic history, where we can see so much, may be uniquely privileged. We must treasure it, for it will not last. But is this cosmic isolation tragic or liberating? It means that knowledge is both time-bound and beautiful. Every discovery is a gift, and every unanswered question a precious link to a universe we will one day lose. 7. The possibility of infinite life and infinite stories. Return to the principle of cosmic repetition. Given enough space and time, every possible planet, life form, and even story must repeat. If the laws of physics permit life, then life must exist everywhere that physical niches arise, not just in trillions of galaxies, but in infinite places. Evolution becomes a cosmic law, not an earthly accident. There must be civilizations far more advanced, and others at primitive beginnings. Infinite variations on consciousness, self-awareness, technology, and culture. Literature and philosophy confront this with both wonder and apprehension. Are there great filters, barriers that most civilizations never pass? Or is consciousness a universal, inevitable property? With infinite worlds, is every story, every triumph and tragedy, every emotion played out somewhere, countless times? The idea of infinite stories, infinite lives, and infinite possibilities is thrilling and daunting. It renders every triumph universal, every tragedy transcendent, every moment a jewel set among endless permutations. 8. Free will, meaning, and cosmic identity. With infinite repetition, philosophical puzzles about identity and free will grow sharper. If every choice and every possible outcome occurs somewhere, what does free will truly mean? Are we alone, or always one among infinite selves, infinite histories? Science does not resolve these questions, but it deepens their texture. Our sense of self is local, a product of biology, consciousness, here and now. Infinity suggests we are both unique and universal. Every moment is mirrored, every life is repeated, yet every conscious experience is singular. Meaning, perhaps, is not found against the backdrop of cosmic rarity, but in the act of living. To see yourself as both the center and a part of an infinite whole is a radical shift, a posture of cosmic humility. 9. The simulation hypothesis and mathematical universe. Fascinated by infinite repetition, some thinkers, Max Tegmark among them, propose the mathematical universe hypothesis, that reality itself is a mathematical structure, and all mathematically possible universes exist. In this view, our universe is one mathematical entity among infinite others. The simulation hypothesis suggests that, in an infinite cosmos, real and simulated universes may coexist or be indistinguishable in terms of conscious experience. If so, questions of existence, consciousness, and reality become intricately woven. What is real in an infinite array of mathematical and virtual existences? Is science the method for describing the actual or just the most probable? This plunges us deep into metaphysics and philosophy, but is inspired by the very scientific implications of cosmic infinity. 10. Gravity, black holes, and the preservation of information. Modern physics finds its greatest paradox in black holes, objects so dense that not even light escapes, yet whose existence and properties challenge the very notion of cosmic destiny. Stephen Hawking famously showed that black holes emit Hawking radiation and eventually evaporate. But the question of information persists. If matter is lost into a black hole, is the information about it lost forever? Or is it preserved somehow in the universe's fabric? In an infinite universe, this puzzle persists at endless scales. Some theories say that information isn't destroyed, but encoded in subtle patterns, linking quantum mechanics, relativity, and cosmology in a grand quest for unity. The fate of information in an infinite cosmos may even relate to the fate of consciousness and physical law. 11th, cosmic causality, the anthropic principle, and our place. Why does the universe allow for life at all? The anthropic principle holds that some features of the cosmos are fine-tuned to allow for observers. In an infinite universe, this principle gains new depth. Given infinite possible regions and configurations, some must allow for consciousness, intelligence, and even curiosity. We observe the universe because we exist, and we exist because the universe allows it, not by special creation, but by infinite possibility. This is not a meaningless circularity, but a powerful statement about probability. Infinite universes guarantee the existence of observers. Cosmic causality is structured by possibility rather than necessity, and this, in turn, redoubles the meaning and humility of our self-awareness. Life is not inevitable everywhere, but inevitable somewhere, in infinite places. The edge of knowledge, science's deepest frontier. All these implications remind us that science is, first and last, the pursuit of knowledge, always at the edge, always humbled by what cannot be measured. Every discovery pushes the horizon outward. Every unanswered question marks both our ignorance and our hope. The edge of the observable universe is the edge of evidence, never the limit of existence. We glimpse only a fraction of the cosmos. There are whole domains whose laws, histories, and fates are beyond our current reach. Mind-bending implications? They are the currency of modern cosmology. They remind us that knowledge is a journey, not a destination, and that mysteries are both invitation and perpetual challenge. 13. Science fiction and the infinite cosmos. From the earliest tales to cutting-edge science fiction, infinity and repetition have been themes of inspiration and hope. Vast civilizations spanning galaxies, lost worlds of unimaginable variety, alien minds with physics beyond ours. The possibility of parallel worlds, alternate realities, and time loops, all grounded in the real mathematics of infinite space. The difference today? Science fiction is no longer remote from science fact. Ideas like multiverses, simulations, black hole information, cosmic repetition, all take root in physics, math, and cosmological theory. Dreams of infinite adventure, of journeys beyond the edge, are now both metaphor and scientific exploration. 14. Human meaning in an infinite universe. When faced with infinity, what becomes of human meaning? Does significance evaporate, drowned in endless repetition? Or does it shine brighter against the cosmic backdrop? The answer is deeply personal, but science offers guidance. Our actions, feelings, choices matter. Because consciousness has emerged among infinite possibilities, not in spite of them. Each experience is both singular and universal, a jewel among endless stars. Infinity does not erase meaning. It amplifies it. Against the endless, every moment is both fleeting and eternal. Every discovery, both ordinary and profound. 15. The paradox of purpose and destiny. The implications grow even deeper. What is our destiny? As beings aware of the infinite, is their purpose in a cosmos that is endlessly repetitive, that offers no special center, that may outlast everything we can imagine. Purpose, in this framework, is not given. It is made, discovered, shaped. Our quest for knowledge, our struggle for understanding, our awe and wonder are, in themselves, cosmic phenomena, tiny dramas playing out against a backdrop of eternity. And the paradox is profound. The infinite undermines the myth of cosmic specialness, but empowers the freedom to create our own meaning. Destiny is not granted from outside, but chosen within, a project of consciousness and curiosity. 16. The spiritual dimension, awe at the edge. Finally, deep implications are not only scientific, they are spiritual, existential, and poetic. Awe, wonder, humility. These are the gifts of cosmic perspective. To look at the night sky, to contemplate infinity, is to touch the deepest sources of joy and humility. In the vastness, we are small. In the endlessness, we are brief. But in the very act of questioning, imagining, and yearning, we awaken the force that stretches farther than light. The human drive to know, connect, wonder. Our minds are the universe, become aware of itself. Each thought a tiny echo of cosmic history. Epilogue. Embracing the infinite. So what are the mind-bending implications of an infinite, edgeless, ever-expanding universe? They are, in truth, the greatest source of adventure available to humanity. The certainty that we are not alone, nor unique, but part of an endless fabric of existence. The realization that the edge of knowing is always provisional, a challenge to explore, to discover, to question. The gift of awe, the humility to honor what lies beyond, and the courage to peer ever further into the dark. We are, in the deepest sense, children of infinity, star stuff, with consciousness, observers at the edge, insatiably curious. Every fact of modern cosmology is, at heart, a summons, a call to astonishment. Infinity promises not despair, but hope, not repetition, but unceasing adventure. What we know is staggeringly beautiful. What we do not know is unimaginably vast. And so, let's keep exploring. Let's keep questioning. Let's never fear the infinite nor the edge, because in the journey between them, in the paradox and the possibility, is the pulse of human wonder, mind-bending, eternal, and forever unfinished. As we reach the end of our cosmic exploration, remember, our universe may stretch endlessly, its mysteries exceeding even our boldest imaginations. The paradox of an infinite universe with a shifting edge isn't just a scientific puzzle. It's an invitation to think bigger, to wonder deeper, and to embrace humility at the frontier of knowledge. We stand on a tiny world, gazing out across billions of light years, aware that what we see is only a fraction of all that exists. Yet, it's this very mystery that fuels our curiosity and binds us together in the shared pursuit of answers. If today's journey challenged your perspective, sparked your awe, or deepened your questions, don't forget to subscribe to The Lazy Cosmos for more deep dives into space, science, and the mysteries beyond. Your curiosity is the engine that drives our voyage, and together, there's no edge to where our wonder can take us. Keep searching. Keep asking. Stay cosmic.